So metal halide perovskites, in fact, refer to a large family of crystalline materials, normally with a structure similar to that of the natural mineral called calcium titanate, which in fact discovered by Gustav Rose in 1839 and named after a Russian mineralist, Lev Perovsky. So metal halide perovskite, in fact, can be described as a general chemical formula of ABX3, where A is the monovalent cation, B is the divalent metal cation, and X is the halogen anion that normally bonds with the metal cations, and they normally form corner sharing BX6 4 minus octahedral cavities. And this embedding the A cations as well. So halide perovskite, in fact, brought a paradigm shift to the semiconductor field, where in comparison to the conventional semiconductors such as silicon, which requires to be almost defect-free in order to be sort of efficient in the electronic devices, and they normally fabricated with complicated, costly manufacturing processes. However, perovskite could be processed simply by printing, similar, for example, to newspapers, with relatively high number of defects, but performing still as good as or even better than the conventional semiconductor. So this is quite a paradigm shift in the semiconductor science. And halide perovskite is a highly tunable and high performance semiconductor, and in particular for PV application, perovskite solar cell is known as the fastest growing PV technology, where its power conversion efficiency jumped from 3.8% to 25.7% within just a decade. This is quite significant if you compare it to a conventional semiconductor-based solar cell like silicon solar cells. So perovskite PV also offers ultra low-cost energy generation. This is because of their inexpensive and abundant precursors material, and also it's because of their inexpensive and versatile processing at low temperature in particular, compared to like silicon solar cell, which normally produce at very high temperature, about 900 or 1000 Celsius degrees. So perovskite PV also provides novel PV applications, such as flexible lightweight photovoltaic panels that could be used in electric cars, for example. They also offer applications for colorful sort of solar windows as like a colorful PV panels. Also, perovskite PV offers applications for indoor photovoltaics for use in Internet of Things, IoT, wireless sensor networks, and also consumer electronics. So that's all in all makes perovskite photovoltaics very interesting PV technology that is emerging and coming to the market slowly. So basically, in order to maximize the efficiency and stability of halide perovskite-based solar cells, it is extremely important to minimize the defect density and also to maximize the luminescence efficiency and radiative recombination. Just to give a context, basically we have different kinds of recombination. One is radiative, means when electron holes are recombining, they generate the photons. And the other one is non-radiative, and that means basically the recombination causes a heat, which is normally wasted. So that what we want in optoelectronic devices is to maximize the radiative recombination. So, or on the other hand, to minimize the non-radiative recombination or losses in the devices. And in the perovskite solar cells, these non-radiative recombinations are normally originated by the ionic defects, which is normally like a halide vacancy or subband gap charge carrier trap states that mostly exist on the grain boundaries within the perovskite sort of crystalline structure. So one of the most effective ways to reach this goal, I mean, to maximize the radiative efficiency in perovskite semiconductors, is to utilize monovalent cation additives, such as alkali metal halides. And this is because of their loading capacity and also their chemical compatibility with the perovskite materials. I should mention that halide perovskite are remarkably tolerant to additives. compared to conventional semiconductor such as silicon. This is mainly because of their unique crystal structure and also their band structure, which can accommodate additives without sort of compromising their properties. So this, in fact, give us or provide us with a wide range of creative space for additive engineering in order to maximize the performance of perovskite optoelectronic devices, which include solar cells or LEDs or detectors. So all in all, additive engineering, in particular halide additives, metal halide additives, it's a great sort of approach in order to reach high efficiency and stable perovskite solar cells. So when we add metal halide additives into the perovskite system with the ABX3 formula, the metal cations could actually directly impact the A or B site based ions, and also it can impact on the ionic radii and its valence sort of bands in the band structure of our perovskite semiconductor. So the halide will be incorporated in the X site, which is the anion parts of our perovskite. So the incorporation of the metal cations could be normally in the form of doping, which could be interstitial or substitutional, or the formation of alloyed structures. So most metal cations are mismatched to sustain a photoactive ABX3 perovskite with an sort of appropriate Goldschmidt tolerance factor, which is normally between 0.8 and 1. And this makes it sort of to be quite selective on which metal halide additives could actually work in these sort of perovskite semiconductors. So my work with sort of on monovalent cation additives was one of the first report on additive engineering in halide perovskite field, where I initially started with sodium, copper, and silver-based halide additives. Then I found after looking at sort of a series of other metal halide additives, I found potassium iodide is in fact a better candidate to improve both efficiency and also stability of the perovskite solar cells. To discuss about the mechanism of improvement of solar cell by adding these monovalent halide additives. So basically, we observe a significant amount of halide vacancy at the grain boundaries in the pristine perovskite thin films. So just to define that, pristine means without additives. So this causes both ionic migration, which is a big issue in the halide perovskite. So that means ions move within the structure, and sort of therefore the properties of the materials does change by moving the ions, and also cause non-radiative recombination. This vacancy causes non-radiative recombination of charges that in turn reduce the power conversion efficiency of our solar cells. So what I found by decorating the grain boundaries and surfaces within the perovskite by potassium halide layers, so we could achieve mitigating non-radiative losses as well as sort of photo-induced ion migration in the system. So what happening is the excess halide from the potassium iodide that we are introducing into the system actually fill the vacancy at the grain boundaries, and therefore this will passivate the non-radiative recombination pathways. So more importantly, these excess halides are immobilizing sort of in the form of benign potassium-rich halide species that's normally located at the grain boundaries and the surfaces within the perovskite thin films. And this will actually prevent the halide migration at the grain boundaries and surfaces. So just to simplify this potassium iodide additives are actually help the extra iodide that we are introducing into the system is actually fill the vacancies that exist in our pristine films, and the extra potassium is actually bond with the extra halide at the grain boundaries, and therefore prevent them from moving within our sort of semiconductor. So this was actually a breakthrough in the field, because this approach not only enhanced the power conversion efficiency of our solar cell by minimizing the non-radiative decay, but also stabilize the perovskite band gap because normally when ions move, then the properties of the semiconductor change, and therefore the band gap changes, which is undesirable for a lot of optoelectronic application. And this achievement or this discovery actually helped not only with PV application, but also for other optoelectronic applications such as light emitting diode devices, which actually we proved as addition of this potassium iodide into perovskite LEDs also help with both enhancing the efficiency of the LEDs, also with the stability of them. So basically, metal halide additives have remarkable positive impacts on the crystal growth and also on the optoelectronic properties. And therefore, subsequently, because of these improvements, this impacts on the performance of our perovskite solar cells. So to dig more into the sort of properties of the thin films, so these additives actually help with the control growth of the perovskite thin films and enhances the grain structure. For example, we are forming larger grains, and also we are forming a better thin films in a sense that they are more homogeneous, and also they are pinhole free. So basically, pinholes is a killer of our normally devices, energy devices like just solar cell or LEDs. Because if you have a pinholes in your thin films, then there will be a sort of a short in your device because of the opposite contacts will have direct contacts. And these additives are in fact helping with forming a very homogeneous and pinhole-free thin films in our sort of devices. So other pressing challenge in perovskite-based optoelectronic devices is when we actually interface our perovskite thin films with contacts or charge transport layers. Just to give a context, for any sort of optoelectronic device like solar cell or LEDs, basically our perovskite thin films is sandwiched between two charge transport layers. One is for electrons transport, one is for holes. So we call it electron transport layers and hole transport layers. And it's very important that when we actually interface our perovskite thin films with these transport layers, that we preserve the properties of our thin films and sort of the quality of our semiconductor. It's important to preserve the quality, and it doesn't change when we sort of add an extra interface to our system. Unfortunately, this is not the case. And when we observe that when we sort of add an extra interface to the perovskite, like electron or hole transport layer, the properties actually reduce. In particular, one of the key properties, which is a measure of the quality of semiconductor in device configuration, so-called photoluminescence quantum yield, drops significantly when we interface our perovskite with the contact layer. So to address this challenge, again, our approach in addition of potassium iodide into the system works quite well in this scenario. What actually happens is this potassium iodide, which is a monovalent halide additives, creates or form a self-assembly potassium halide based monolayer at the interface of perovskite with the other charge transport layer in our devices. And this actually enhances the interface between the perovskite and the contacts quite significantly. And we were able to preserve the PLQE quite significantly in a sense that PLQE drop much less compared to when we don't have the potassium iodide in our system. So this subsequently led to more efficient and also a stable perovskite solar cells. One of the downfall or in our perovskite solar cell is because of these sort of not perfect contacts with the charge transport layers. The ions actually can move across the layers, for example, from the perovskite into the hole transport layer. And we observed that this monovalent halide additives can can prevent not only the ion migration within the perovskite, but also can contribute towards preventing the ion migration towards other layers within our optoelectronic devices, such as LED or solar cell. So just to summarize, so utilization of these halide additives, which we talk quite a lot about, the potassium iodide as just one example, is a very important and effective approach to not only enhance the power conversion efficiency of our perovskite-based optoelectronic devices, but also it's important to make them stable, to enhance their lifetime, which is a key aspect for a lot of commercialization applications, ranging from the rooftop panels, solar panels, to IoT devices, and also consumer electronics.